selection lab. It's probably gonna take the whole week, so we'll see. But I want to start phylogenies today. We might finish it tomorrow. Yeah.
Yeah, where again?
Phylogeny. Phylogeny, that's what you say. Okay. So, in Living Earth, you probably learned the levels, right, of taxonomy. Is that right? Did you?
No. It's not in the book.
Huh?
Gosh.
No? Okay. Well, let's define systematics. Okay. So, systematics is the classification of living things. Okay. Humans like to organize, right? We like to organize thoughts and ideas. And so systematics came about when we're talking about how organisms have evolved from one another. Okay. Are they gonna let her in? Alright. Taxonomy is the naming and classifying of organisms. Okay, so we have systematics, which includes relationships and taxonomy. Okay. In Living Earth, you might have learned about domains, kingdoms, phylums. Does any of those names sound familiar? Some of them, maybe? Yeah? Okay. So, all life we can categorize into 3 domains. Okay? One of them is eukarya. That's the one that we're in. That includes all eukaryotic organisms. So all organisms whose cells have nuclei. Okay? The other 2 are both prokaryotes. One of them is bacteria, which I think you're all familiar with. The other one is archaea. Okay. Archaea are similar to bacteria in that they're unicellular and prokaryotic, but they're actually more related to us than they are to bacteria. Okay. So, taxonomy is how we organize things. I like to think of taxonomy like a big filing cabinet. Okay? If you have 3 filing cabinets, each one of them is a different domain. Right? Within those filing cabinets, you may have different drawers, and each one of those is a kingdom. Does that make sense? So this kingdom over here is not in this domain because it's not in this filing cabinet. Does that make sense? Yeah? So within each of these kingdoms, you may have a folder, and that's the phylum. Okay. And then within each of those, you may have subfolders, and it goes down and down until you get as specific as we can get, and that's, the species level. Okay. So we get more and more specific as we go down in the taxonomy. Okay. I don't know if taxonomy is on their AP bio exam. Do you know?
Taxonomy?
Yeah.
Not a huge amount, but I mean, more possibly in an FRQ than in
Multiple choice.
multiple choice.
So, I have a mnemonic. Do you guys know what mnemonics are? Like words you make up. You all know what PEMDAS means?
Yeah.
Okay, that's a mnemonic. It means something, right? But you can take out the letters and shorten it into something. Okay, so my mnemonic for memorizing this list in order from most general at the domain level to the most specific is Dumb King Philip came over for good spaghetti.
What?
Dumb King Philip came over for good spaghetti. What does the D stand for?
Domain.
Dumb. It means domain. Okay? Kingdom. That's Dumb King. What's his name?
Philip.
Philip. What's P stand for?
Phylum.
Phylum. What did he do? He came over, so C is
Class.
class, O is order, 4, good, S, spaghetti, species. Does that make sense? I use that to this day when I'm writing out the order. I can't remember it without saying dumb King Philip came over for good spaghetti.
And I do King's plate chess on fine grained sand.
Yeah, so you just have to learn one and you'll use it for the rest of your life if you're in biology. Okay? So phylogenetics is where the relationships come into play. Okay? So we have systematics, which is taxonomy and phylogenetics. Okay? Taxonomy is how we classify things. Phylogenetics is the hypotheses of evolutionary history. Okay? How we think those things are related to one another. Okay? Those are the two major parts. Is everyone good on this one? Okay. So we use phylogenetic trees to show evolution. Those should be your fill in the blank. So we use phylogenetic trees to show evolution. Phylogenetic trees are the things that I gave you the pre-test on. Those are phylogenetic trees. Huh?
Oh, my bad, never mind.
Phylogenetic trees are hypotheses. They can change with more data. Okay. So what do we use to make phylogenetic trees? What do you think we use? What can we use? Okay, traits. What kinds of traits?
Physical traits.
Okay, physical traits. What's another type of trait that we can use?
Genetic traits.
Genetics. Yeah. Sorry. So we use fossil records. A lot of fossil record data is physical, unless we can get DNA from those fossils. Okay, most of it is going to be physical characteristics. Okay. And we use DNA. We can use protein sequences, so protein is in DNA, but made from DNA, right? So we can use protein sequences, we can use DNA. We use homologous structures. We talked about what homologous means yesterday. If you weren't here, you'll have to get the notes from your friends. Oh, are you good? I'll wait. Are we good? Okay. So phylogenetic trees are diagrams that represent evolutionary history of a particular group of organisms. Okay? We can have phylogenetic trees that cover all of life. So this is eukaryotes, archaea, and bacteria. Remember, those are the 3 domains. Right? Or we can have phylogenetic trees that are talking about just one species. And we're looking at that species maybe across the globe and what the differences are between that one species across the globe. Okay? So it can be all the way from the domain level all the way down to the species level. They're similar to cladograms. Some scientists use phylogenetic tree and cladogram mostly interchangeably. Okay, but there are slight differences. Cladograms So time isn't just relative on a tree, there's actual time marks on a scale. Okay. We often use cladograms when we're talking about maybe the evolutionary history that includes a bunch of extinct organisms. So we can see sort of where do they branch off, right, and what organisms went extinct. None of the cladogram or the phylogenetic trees that you looked at in the pre-test were cladograms. None of them had a set amount of time on them. Okay. Are you ready? Yeah? Okay. So on cladograms, you can see that all of these lines here are different lengths. Does that make sense? They're not all at one level. That's the difference mostly between a cladogram and a phylogenetic tree. The lengths of those trees mean something. Okay. So on these, each line represents a lineage. And remember, that lineage could be as small as a species, right, or as big as a domain. Okay, it just depends on what you're looking at. Okay. Each branching point is called a node. Okay. So this right here is a node. This right here is a node. That's 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 a node. Okay? So every time it branches, that's a node. Nodes represent common ancestors. Tell me what a common ancestor is. Because I gave you the definition yesterday. So someone who was here yesterday, tell your neighbors what a common ancestor is.
A population of interbreeding organisms that diverge.
Yeah. A population of interbreeding organisms that diverged or speciated. So each one of those nodes represents a common ancestor. It represents a population of interbreeding organisms that for one reason or another speciated. You can shut the door if they're loud. All right. Nodes and all the branches that come out of them are called clades. So can someone tell me what a clade is on that picture right there? Tell me what a clade is. Yeah.
Isn't it like the branches like breaking them off?
Yeah. So tell me which one's a clade? What's a clade?
Tiger and snow leopard.
Okay, so tiger and snow leopard are a clade. Does that make sense?
Yes.
Because it's a branch or a node in all the branches that are coming out of it. Someone tell me another one.
Tiger and snow leopard.
Huh?
Tiger and snow leopard.
Okay, tiger and snow leopard. Another one?
Is it a lion and a jaguar?
Mm-hmm. Tell me another one.
Leopard,
The
jaguar.
leopard one.
Huh? Say it again. What?
The leopard to the lion and jaguar.
Uh-huh. Leopard, lion, and jaguar. That's clade. Tell me another one.
Tiger and the other one.
Yeah, tiger and snow leopard. We got that one. We got this one. We got this one. There's one more. Huh? All of them. Tiger, snow leopard, leopard, lion, jaguar. They all come out of this node, right? So it's a clade. Okay? Species and clades share characteristics. We call these characteristics shared derived features or shared derived traits. dots are for. It's fine. Alright. The root of the tree is right here. And you can see on it says Panthera. Those are the panthers. Right? So all these are what we would call Panthera. Okay? That root right there represents the common ancestor for all of the species that are in that tree. Okay? So that right there. Do you see the red dot? If I go back, it shows up right there. That's the root. Alright. When two, what we call terminal taxa, so those would be the ones that are coming off of these branch points, if they share a common ancestor together, we call those sister taxa. Okay. So you should label that on your tree. Any of this is right? We have a tree like this. What are these?
Node.
This is a node, right? So if they share a node together, what are they? They're a clade, but they're also sisters. That make sense? That's all that's saying. Okay. So two clades that emerge from the same node are called sisters or sister taxa. Okay. If this is our root, right here, the first one that comes off, we call it basal taxon. Right? We're going to give it another name a little bit later, and that's the outgroup. Okay. What about the branch on there that looks like this? You see it on your tree? The node is right here. So what do we know about this node in these organisms that are up here? Do we know which ones are sisters? Sisters have to have only two, right? Coming out of one. So are there two? There's more than two. Okay? This we call a polytomy. What that means in terms of relationships is that we don't know how those four things are related to each other. We just know that they're related. So we put them all at the same node, and they all come out of that node. Okay. I'm gonna give you some Latin and Greek. Okay. Sin or sim means shared. Apo. APO. Apo means derived. Ot means unique. Plesio means ancestral. Morphe means trait or character. You need to memorize these words, okay? Huh?
What's the top one?
Sin or sin, S-Y-N or S-Y-M. Do you see this picture on your thing?
Yeah.
I want you to put a big cross there. It's not right.
Oh.
It's partially right, but not all the way. Okay. Can you draw? Can I erase polytomy? Yeah. Okay. If this is our tree, okay. First, let me tell you this. These terms, synapomorphy, symplesiomorphy, autapomorphy, they are relative to whatever you're talking about. They can change. Okay? So I'm going to give you an example. If these, it doesn't really matter. Okay. If this basal one is our outgroup, it means it's closely related to these, but it's not part of that group. Okay? So if A, B, C, D, and E were the great apes, what's an organism that's not a great ape but related to great apes? We're in there. We are a great ape.
We are?
We are.
I thought we were.
No, we are.
Monkeys?
Monkey.
Chimpanzee.
Chimpanzees are great apes.
What about those ones with the bubble butts?
I don't know.
Baboons, yeah. they're-
Monkeys, though, would count. Because they're not great apes, but they're closely related, right? They're still primates. Okay? So, if monkeys are here and all the great apes are here, this group right here would be called the in-group. Okay? The in-group is what we are trying to hypothesize the relatedness amongst those organisms. Does that make sense? Yeah?
Yeah.
Okay. So on trees, you all probably saw on the back of your pretest where it had like all those markings on the tree. Those are how we mark traits. Okay? So if a trait appears right here, what does that mean?
Everything has that trait.
Everything on the other side of this mark has that trait. Does that make sense? This trait right here, if it comes before the outgroup, is it shared? Is it shared amongst all of these organisms? Yeah, because if it's marked here, it means everything has it, right? So it would be a sim. Right. Is it derived amongst the in-group? Let me ask you this. Does it tell you anything about how A, B, C, D, and E are related to one another? No, it just tells you that they're related. Does that make sense? Because their common ancestor, which is right here, have that trait. So is it derived or ancestral? It's ancestral. Doesn't tell you anything about how A through E are related, it just tells you that they're related. Okay? That make sense?
Yes.
Okay, what do I add on the end of your 5 terms over there? Morphe. That would be a simplesiomorph. A shared ancestral character. Okay? What if I put a trait right there? Does that tell you anything about how A and E are related, or A through E are related? No. Again, it just tells you that they're related. It tells you that they share that trait. So what would that one be called? Apple means what? Derived. If it's not telling us anything, then what is it? It's a simplesiomorph. Okay. All right.
So, I think they're trying to figure out like, but if there was a branch here, then this would be what you guys are thinking this was supposed to be, correct? This one would be derived then.
Yes, but it all matters based on what you're looking at, and that's not part of the in-group.
Right.
Yeah.
So you guys were like, cause you guys were thinking what's derived, right? The difference is we're getting a branch that is separating this from everybody else. So this is derived for these guys,
Yeah.
but it still has nothing to do with them. You have to visualize what it is you're actually looking at. This
It's
isn't
all
derived.
relative.
Yeah, it's relative to where you're looking on the branch or how big your branch is.
So they're not
Right.
related to the regular branch that they're connected to.
Say that again?
So, because of that other branch, they're not related, right? That one you just erased?
So this one,
Yeah.
there's still a degree of relatedness because they're all related right here. D and whatever this is are still related because of
Yeah.
this,
Okay.
right? The degree of relatedness changes and this may end up way over here if we're looking at genetic combinations versus a physical trait or something. So yeah, these they get tricky and they change. It, like she said, it's all relative to what it is we're looking at.
What's your in-group? That's the first question you should ask. Okay.
When you go through these, all these characteristics, picture picture yourself on a bus, right?
I
And
don't know where you're going with this.
and this bus is going to here, wherever it's going, right? And these are little checkpoints, right? Here's a bus stop. Do you have the ticket? Does your ticket say you get to keep going? Yes. Whatever trait that is, cool, everybody's on that bus. Now the bus is going this way. Well, your ticket doesn't give you permission to ride the bus. Get off the bus. Right? No, you don't ride. That's
Yeah, you
our
don't have that trait.
that's our out group. Everybody that's left now is the in group.
Does that make
Cool.
sense?
And then
So
these
basically, it's discrimination.
you can think of it that
No.
way, sure. These are just
It's just
checkpoints
evolution.
along the way. Do you meet the criteria? Do you, right? Or do you have the bus pass? Can you get through? Yes, okay, cool. No?
So
Not my
like,
boss.
it's whether or
That's
not
how you
it
don't
fits the
have an
needs of whatever
Imagine, yeah,
environment.
that's
What?
why evolution
No.
is
Or-
discriminatory.
So here's the thing. It has nothing to do with any environment. We could be talking about sugar glider in Australia and a flying squirrel in the United States. Right? Has nothing to do with it. This has to do with whatever it is you choose to look at.
Yeah.
Oh.
It's all
Right.
relative.
It's all relative to what traits you're looking at. You can end up with, I'm not quite sure how, but like a snake and a an elephant over here if you just happen to be looking at the right traits, and you can put a snake and elephant next to each other. It's relative to what it is you are looking at. Cool? No two scientists are ever going to make the same one either.
Alright, what is this trait? Is it derived or ancestral?
Sin, apple,
Say it again louder.
Sin apomorphy.
Sin, apomorphy. Does it tell you anything about how A, B, C, D, and E are related?
No.
Are you sure?
Yes.
Because if only D and E have it, does that tell you that D and E are probably more closely related than they are to these?
Yeah.
It tells you something.
Yeah.
Okay, what's this?
It's not even shared. Sin apomorphy. But it's not shared though.
Oh,
Only
sin
they have
let's see
So
all
wouldn't it just be like apple, apple,
Say it louder.
Apple's derived.
It's an ought apomorphy.
apple.
Oh.
Well, you put ought.
Why is it ought?
Because only E has it.
Because only E has it.
Oh.
Is it derived?
Well, yeah.
Does anything else have it?
No.
Yeah, then it's derived, right? They derived that character. Does that make sense? Okay. Does it tell you how anything is related?
Yes.
Does it give you any information?
What do you mean by information?
Does it tell you if I had all of these 5 organisms and I wanted to know how they were related, and I had this one trait that only this organism had, does that tell me how any of them are related?
Yes.
No, because it's not.
Alright, so
No, because it's not shared.
It's not shared.
here's the thing.
It has to be shared characters. Shared characters are the way that you figure out how organisms are related.
A lack of a trait does, because they all lack the same thing, doesn't mean they're related, right? Because all of these guys lack this, doesn't tell us how closely related they are. The absence of a trait doesn't help us. Does that make sense?
Yes.
That's, yeah.
Okay. I'm gonna give you these 2 definitions. We've already talked about them. And I'm gonna say that these okay. Sharks, fish, I changed it a little bit. Amphibians, reptiles, mammals. Okay. What do mammals have that nothing else has?
Warm blood.
Hair. So, if we're looking at mammals right here, and this is our tree, if I put this as hair, what is that? You just told me. It's an odd apomorphy because it's unique to mammals. Does that make sense? This is where the relative nature comes in. Okay? If I took this away and we extended it and it included a bunch of mammals, now what is it? It's a synapomorphy because it's shared amongst all of these and it's derived. Does that make sense? If there's only one branch here, that trait hasn't changed. But what we talk about it has. Right? If this branch right here is just mammals and it just says mammals, that's a an odd apple. If I add a bunch of branches, now it's shared. It's not unique anymore. Does that make sense? So now it would be a synapomorphy, a derived characteristic. And that would tell us that all of these are related. Okay. I don't know where the clicker went. Story of my life. You use sin when you're talking about derive, and you use sim if you're talking about flethio.
And if you think about it, sin, like synthesis, we're making something, so these guys are, right?
Oh.
That's where we get the
It's all the same.
shared. It's shared because it's made together, kind of, that they all together share.
Okay.
I understand now, so.
Did you write these down already? I added another one, ancestral. The next step of this is you're gonna be making your own trees. So we're gonna be giving you traits and you're gonna be making your own trees.
Is the presentation for that due tomorrow?
No, next
week?
Friday.
Okay.
How many of you had me as a freshman? Did you guys do the shoe activity?
No.
The shoe?
Yeah, where you took your shoe off, put it in the middle of the room.
Oh, yeah,
I
I
remember
remember seeing that.
That is this, dude.
What the
Oh, this
heck? That's crazy.
Alright, out group, in group, we already talked about this. I have 3 minutes left.
Always was you just whichever one.
Yeah, your out group is almost always gonna be the first one that comes out. Yep. So closely related to the rest of the organisms, but not part of the in group.